Last week was about finite difference methods. Well, we'll be seeing this week focus on type of method for solving. And personally, my favorite type of method, spectral methods, kind of specialize in for research. There are two kinds of spectral methods I'll talk about this week. One for problems of periodic boundary conditions, that will be today. And then non-periodic, I'll talk about on Thursday. Now, so I'll paint a contrast between main property of spectral methods and finite difference. So FD, my abbreviation for finite difference. What we saw before was the error is proportional to some power of h. For instance, methods we saw last time are proportional to h squared. Okay. All right. Now, but spectral methods. Okay. What we have here is that the so I should say for finite difference is some fixed p. I want to emphasize here. So the spectral, the error is order h to p for any p. So in other words, the error is going to 0 as h goes to 0 faster than any power of h. So another way of putting it is we have exponential convergence as opposed to polynomial order convergence with finite difference. Okay. However, this is not always the case. This is true provided the solution itself, the exact solution, is infinitely smooth. Now, on the other hand, okay, if U is in CP, so there's P continuous derivatives, but no more than that, then we have this polynomial order convergence again. Okay. So, only in the case where U is infinitely smooth, but that's not an unreasonable assumption. For example, the solution of a heat equation is infinitely smooth. So we can observe this kind of convergence. Okay. All right. Now, there is a trade-off when it comes to spectral versus other kinds of methods like finite difference. So, the conventional wisdom on spectral methods is that on the pro side, as I just mentioned, rapid convergence. But a drawback is that they're limited in applicability. Now, for those problems for which they are most suitable, they're really the best method you could hope for. It's that's a relatively narrow category. Now, what kinds of problems are they best suited for? For PDEs that are linear. Also, simple domains. Like, for example, in 2 dimensions, a rectangle or rectangular domain is fine, or a circle, something like that. But like, just if your domain is an irregular shape, then spectral methods are not a good idea. Okay, and also simple boundary conditions, such as periodic or homogeneous geometry boundary conditions, things like that. But for complicated boundary conditions, you might want to use something else. Okay. Okay. I will say though that there's one other criterion that used to be also on this list, and that is best for problems with constant coefficients. And there's some who still believe that, but I would say that's no longer true simply because of my own spectral methods, which are specifically designed for problems with variable coefficients. So I struck that from this list. So I guess that's the main contribution of my research program. So make spectral methods a little more useful than they were before. Okay. All right. These are best methods for problems for which they are suitable. Okay. All right. Okay. Now, another distinction between spectral methods and other kinds of methods, such as finite difference or even finite elements. Spectral methods are what are called non-local. For a purpose of approximating derivatives. Now, what I mean by that is finite difference and similar methods are local in nature in that they approximate derivatives using only nearby points. For example, second derivative is center difference. You're trying to compute a derivative at some point x naught. So you use the value of a function at x naught plus h and x naught minus h for some small h, and only those points. So only nearby points. Whereas spectral methods will use all of the information about the solution on the entire spatial domain to approximate a derivative. It'll end up doing so more accurately than a local method, which is how we realize this exponential convergence. Okay. All right. Any questions up to this point? Yes.
Right, so I'm wondering what simple boundary conditions means. Whether it's got something to do with it being periodic.
Periodic's one example, or like homogeneous Dirichlet or normal boundary conditions. If you have non-homogeneous boundary conditions, you could try transforming a problem so that it is homogeneous, although that's more difficult in some cases than others. Like, if that's pretty simple to do in one space dimension, but in higher space dimension, you might not be able to. There are other more nefarious kind of boundary conditions, like absorbing boundary conditions, where you're trying to simulate what's happening on an infinite domain. You have a wave propagating, and here's your boundary. And physically, if a wave should continue, it should not like reflect back or anything. So you can come up with an absorbing boundary condition to implement that, but it's difficult to use that with a spectral method. So, yeah. Questions? Okay. Now, so now I'm going to focus for the rest of the time today on a particular kind of spectral method for a periodic case. All right. Okay. So, okay. So, I like to assume that function u of x that is 2 pi periodic. Okay. And I'm going to define a grid, my spatial domain, xi is equal to I times h is equal to 2 pi over n, where n is the number of grid points. And I goes from 1 to up to n. So what this means is the left boundary point at x equals 0 is not included, but the right boundary point at x equals 2 pi is. So this is how gridding works for periodic boundary conditions. You include one boundary point or the other. I've seen different choices made in different books. Because whatever boundary point you exclude, you still know the value of u there, because you can take it from the other boundary point because of the periodicity. Okay. Yeah.
Left isn't included, right?
Yeah. So. Okay. All right. Now, because it's 2 by periodic, U has a convergent Fourier series and the UK hat are the Fourier series coefficients. Right. Well, this is unfortunate. Okay. I think I need to use slightly different notation here because I used UK hat for another purpose later on. So I'm going to write this differently. U hat of k, I think it's a function of k, where k is an integer. Or negative. All right. Now, but the thing is, we might not have a formula for u of x. Generally, we won't in the numerical setting. We may only have a vector of values of u at the grid points, in which case I can't use that formula. I really and have a, also we have infinitely many terms here, which of course is not practical. So our approximation that we'll use on the grid is uj, which is an approximation of u at xj, is a similar sum where you consider only a finite number of frequencies. And I'm assuming for convenience that n is even. Then we have e to the I k xj, so we're evaluating this at this point xj, uk hat, where uk hat is an approximation of the true Fourier coefficient. We're approximating this integral by a sum. For k equals, we have a range of integers that is, as much as possible, symmetric around 0. So exact u, approximate u, truncated Fourier series. Exact Fourier coefficients, approximate Fourier coefficients. U minus h is 2 pi over n. So that's corresponding to like the delta x, representing the dx from the integral. Okay. Now, how to get these coefficients efficiently? Use the fast Fourier transform, or FFT. So if you have a vector of the values of u at these equally spaced grid points, you actually have a MATLAB function called FFT that would compute these values for you very rapidly. Because if I were to compute these in the straightforward fashion, like evaluating all of these summations, I have n values uk hat, I have n values of u coming in. You think this is a matrix vector product where these are the matrix entries. That would take order n squared floating point operations. So that's pretty slow. But if I use the fast Fourier transform, it would take order n log n floating point operations or fly. So it's a lot faster, especially, and that advantage increases as n gets larger. Okay. If I have these values, then I can get these to uj using the inverse FFT. So like the MATLAB function IFFT will go from these to these. Okay. All right. So the goal of the spectral method is to approximate u prime, so approximate the derivative, and I'll focus on the first derivative, but this will extend to higher order derivatives using all the grid points that are just ones nearby. Okay. Now, when it comes to numerical differentiation, the conventional wisdom is the approximation of a derivative is the exact derivative of some kind of approximation. So finite difference schemes, what you're doing is you're approximating your function locally by a polynomial. And you're taking the exact derivative of a polynomial. And that's how we get these finite difference formulas that I showed you last week. Here we're going to use a different kind of approximation, but again, take its exact derivative. I can compute p prime of x, where p of x is really just this truncated Fourier series. Okay. Now here, I've evaluated this at only the grid points, but now I'm thinking of it as a function of x defined on a continuum, the domain, the spatial domain x going from 0 to 2 pi. So, so if I can just compute the exact derivative of this, but I want it to be in terms of not these Fourier series coefficients, but the values of u at the grid points. Because with a finite difference case, you have values of u at select points. You take some linear combination of them, and there's your derivative. I want the same thing in this case. It's just that here I'm taking a linear combination of more points. I should mention that this function p of x is called the band limited interpolance, BLI, of u of x. So it's interpolant because p of xk is equal to uj for all indices j. So it matches the data that you have on u. So that's why it's called an interpolant. It's a band limited interpolant because we're only using a limited range of frequencies, whereas a true Fourier series uses all frequencies from minus infinity to infinity. So when you cut it off at a certain point, that's called band limited. And if I write this exponential as e to the ix raised to the k power, this is just why this kind of function is called a trigonometric polynomial. Which can be written in terms of sines and cosines. Sine or cosine of k times x, where k is an integer, as opposed to a conventional polynomial, which has powers of just plain old x. Right. Questions at this point? Okay. So to figure out the derivative of this, in terms of my values of u, I'm actually going to use a variation of something we've seen before, but Dirac delta function. We'll call this the discrete delta function. Delta J equal to 1 if J is equal to 0 mod n, meaning it's so J is an integer multiple of capital N. It's equal to 1, 0 otherwise.
I don't get the zero mod.
Okay. So, so J is meant to assume values from 1 to n. But we're going to see when we do indices, we might get indices that fall outside of that range. So when J is equal to 0, n, 2n, 3n, etc., or minus n, minus 2n, that's when it's equal to 1, otherwise 0. Yeah, so it's a delta function with period that wraps periodically. All right. So using its delta function, I can write uj as a sum from n equals 1 to n of um delta j minus m. So the idea is, so j is an index between 1 and n. So if I have j and m varying between 1 and n, only when it's different to 0 is it's equal to 1. So it selects the proper point, which will be uj. But uj is the same as p of xj, because this is a band-limited interpolant. Then I can rewrite the sum as this would be p of xj minus xm. Okay. Well, actually, all right. Where pj is a band-limited interpolance of delta j. Because this right here, if I plug in xj here, when this is 0, in other words, when j is equal to m, I want this to be 1, otherwise 0. So pj of x m is equal to 1 M is equal to 0. 0 upwards. Fine. The mod is also necessary because all the functions we're dealing with here are 2π periodic. So if this is not a function that's only going to be 1 at a certain point and 0 on the entire real number line, it's going to wrap 2π periodically. Okay. So how this helps me is my derivative that I'm looking for, which is approximated by p prime of xj, is given by taking a derivative of this sum. So it all boils down to this. I need the derivative of this. Okay. Okay. Now, so how am I going to get that? Well, pj of x, I can express it as what? Or repeat, I can express pj in terms of a Fourier series. I'm sorry, what was your question?
No, I was thinking of that.
Okay. So writing it as a Fourier series, it's truncated. Okay. I'll have delta k hats e to the I k x. Okay, and now I need to define that. Well, delta k hat is the discrete Fourier coefficient of my discrete delta function. So that is sum okay. And h on the outside, I have delta j e to the minus I k xj. So this is exactly the approximate Fourier series coefficient formula that I gave earlier. But this is equal to 0 unless j is 0. Okay. Now, but when xj is equal to j times h. So when j is equal to 0, I have e to the 0. So this whole summation collapses to 1. So this Fourier coefficient is h. So in other words, all the Fourier coefficients of a discrete delta function are the same. They're all equal to h. All right. So now I can include this back in here. And I just have, I'll pull the h outside as a constant. So this is my band limited turbulent of delta j. So my goal now is to get a formula for this that's more concise. It doesn't involve a summation. If I get a formula for this function, then I go ahead and take its derivative. Now, I can take the derivative of this with respect to x, of course. The trouble is, it's still a summation. That's not going to be very efficient. If I could express this as a single term, that would be preferable. Okay. Now, what I can do is rewrite this exponential, this complex exponential, in terms of sines and cosines. Now I have h over 2 pi sum I'll have cosine of kx plus I sine kx. Actually, what I need to do is I should break it up into two sums. That's 0. Reason why is that's the imaginary part. Pj of x is a real valued function. Now what's left is to come up with a more concise expression for the sum of cosines. Now every time I teach this class, I love to do this part because it's fun to work with the trig identities to work out that expression, but I don't want to gobble up all our time doing that. Unfortunately, I'm just going to have to cut to the chase. So what we have is h over 2 pi, that's sitting outside. And then that sum of cosines turns out to be equal to sine of pi x over h over tangents of x over 2. Now, of course, we know that tangent can be equal to 0 at certain points. Tangent is equal to 0 tangent equal to 0 wherever sine is equal to 0. So in other words, x over 2 is an integer multiple of pi. So in other words, x is an integer multiple of 2 pi. But sine will also be, let's see. Okay. Well, we're considering a domain 0 to 2 pi, so we're covered in the interior anyway. Now, it seems weird here. H is equal to 2 pi over n. So, okay. Well, so this is actually equal to nx over 2. So, So in other words, wherever the denominator is equal to 0, the numerator is also equal to 0. It's a 0 over 0 situation, which is the indeterminate form. But it can be shown from there that you can get a finite value by taking the limit as x approaches one of those points. But it's not really this that we're interested in. It's the derivative of this at each grid point. But are there any questions up to this point? Okay. We're almost there. All right. Before we get, after using a quotient rule and simplifying as much as we can, Pj prime at some grid point xk is equal to 1/2 minus 1 to the k cotangent of kh over 2. So now, that means my approximation u prime at whatever grid point, which is equal to the exact derivative of band limit interpolative of u at that point. And that was, just to refresh your memory, that was written as sum over m um Pj prime x j minus xm. So now what I can do is I can use this formula right here. But times 1/2 minus 1 to the j minus m cotangent of j minus m h over 2. Okay. So these are the coefficients of in my approximation of u prime at xj. In other words, these coefficients make up my stencil. Now, unlike finite difference stencils that only have a handful of coefficients in them, here we have n coefficients altogether. In fact, you can think of this as a matrix vector product. A matrix with this entries times a vector of u values gives me my u prime values. So, in other words, I have vector w is equal to du. So wj, my approximation of u prime of xj, and the vector u is my vector of u values. I'll put a subscript n for number of grid points. And the matrix Dn is matrix where all diagonals have the same element on them. So we have zeros. Oh, I should mention there's a mistake in here. Notes. Okay. Oh, never mind. Okay. We have zeros all the way down the main diagonal. And then on the right above the main diagonal, we have 1/2 cotangent of h over 2. Right below the diagonal, we have minus 1/2 cotangent h over 2. And then the next diagonal would have minus 1/2 cotangent of 2h over 2. Here I'd have negative of that. So as I keep going, I'd have like h over 2, 2h over 2, 3h over 2, 4h over 2, alternating signs. And the lower triangle is the negation of the upper triangle. In other words, it's a skew symmetric or anti-symmetric matrix. Now, that may not be the most practical way to actually compute the derivative by forming this matrix explicitly and multiplying it by it, because that would take order n squared operations again. And work with that, which I'll show you in a little bit in an example. Okay. Okay. So we do FFT of u, which gives you a vector u hat involving Fourier coefficients. Then, if I define WK hat equal to IK UK hat, and then I take the inverse FFT of W hat. That would also give me the derivative. And this takes order n log n operations. Whereas actually forming this matrix and carrying out this matrix vector multiplication, order n squared floating point operations. The reason for the multiplication by IK is because the derivative with respect to x of e to the IKX is IK IKX. So that's why the Fourier coefficients of a derivative have this factor of IK in them. The order of accuracy. Order h to the n because of using n grid points. But n is equal to, so we have h is equal to 2 pi over n. So n is equal to 2 pi over h. In other words, it's proportional to h to the 1 over h. So as h goes to 0, the exponent is going to infinity. So this is going to 0. That's of an a power of h. Assuming that the function you're taking a derivative of is smooth, infinitely smooth. So that's what gives spectral methods its superior accuracy, using all the grid points to approximate the derivative. And if you compute derivatives using like the FFT, then it's still a quite efficient algorithm. this matrix is in the notes. There's a similar matrix in the notes. If you take the square of this, then you have a matrix that will give you second derivative. That'll be helpful in one of the homework problems because it's a homework problem 4. Oh, wait, no. I'm thinking of the non-periodic stuff that I'll cover on Thursday. That has a separate differentiation matrix for non-periodic boundary conditions. Any questions about what we have here? One thing that's kind of strange is, like here we have a diagonal entry as being 0. That corresponds to j equal m. But cotangent of 0 is undefined. So I found that a little puzzling. And I remember looking into this a few years ago, and I don't really remember very well what happened, but I think what I'd done was gone back to the original formula for Pj of x, because this comes from a derivative of it, and seeing that as x approaches 0, that you actually do have like a local minimum, local maximum at that point. In other words, the derivative, so this derivative at 0 really did turn out to be 0. This formula notwithstanding. So yes, it seemed kind of contradictory, but oh well. That was a while ago, and I don't remember it very well. I may have to look into it again just to refresh my memory. Okay. All right. I want to give an example of using this approach to solve a PDE using this kind of Fourier spectral method. And everything I've shown you here is for one space dimension, but you can take the fast Fourier transform in any number of spatial dimensions. So like MATLAB is a function FFT2 for 2-dimensional FFT. And also the separate function FFTN for BFFT in any number of dimensions. So I'll describe for you a 2-dimensional example. And one of the homework problems, part of problem 5, will feature a 1D version of this 2D problem we're going to show you now. Okay. So as usual, Poissons. So you have minus Laplacians, the u of x plus uyy equal to fxy. On our domain omega, which is square from 0 to 2 pi, 0 to 2 pi, both x and y. And then we have u is 2 pi periodic in both the x and y directions. So in this case, the Fourier series of f will be a double summation of 2 indices k and l, all the integers. Pat kl e to the I kx plus ly. So in one dimension, we just have e to the I kx, but then we have another term in the exponent corresponding to y. And then u of xy will have that same kind of Fourier series. So what I'm going to do is take the Laplacian of this and set it equal to this. So minus Laplacian. The sum u hat KL. I'm going to take the Laplacian of this. Well, if I take the derivative of this with respect to x twice, I'm going to get the quantity ik squared. But that's minus k squared. But I'm taking minus Laplacian, so I end up with k squared for taking the second derivative with respect to x. And then I take second derivative with respect to y and get il quantity squared. Well, that's minus L squared. And a minus makes the plus. So now I have this. So taking the negative Laplacian just multiplies by the sum of squares of the frequencies. Oh. Yeah.
Stuck on step number 2. Where we got the UX for it?
This?
Yes.
Oh, we're just assuming that because all these functions of order 2 by periodic, they're both going to have Fourier series. So we just assume it has that form. Now, minus Laplacian of u is supposed to be equal to f. So here we have Fourier series in the same form, same exponential. So if the two sets of Fourier coefficients are supposed to be equal. So that tells me that u hat KL must be equal to f hat KL divided by k squared plus L squared. Just by setting the Fourier coefficients equal to each other. So this part, these must match. So I just solve for u hat KL. Because f is a function that's given. But what's the one problem with this solution formula? Where does it break down? And we consider how u hat KL needs to be computed. So all we're going to do is, so our solution process is we take the fast Fourier transform of f to get these coefficients, use this to get the Fourier coefficients of u, and then inverse fast Fourier transform to get u of xy. But what's wrong with that formula? Where might I have trouble computing u hat KL? Yeah, I need to require that KL not both be 0. One of them 0 is okay, but I can't have both of them, wait, not equal to. Yeah. So in fact, we have conditions regarding existence and uniqueness. For one thing, we have no uniqueness. So u hat 0, 0 can be set to anything. And it will still satisfy the PDE, you'll still satisfy periodic boundary conditions. Furthermore, we only have existence provided that f hat 0, 0 is 0. Another way of putting it, there's no constant term in the Fourier series for f. That is, f must have a 0 mean. Because if k or L are non-zero, this function, e to the I kx plus ly, has a 0 mean. If you integrate this function over the domain 0 to 2 pi squared, you'll get 0. unless K and L are both 0. In which case you would get the area of a square. So as long as your right-hand side, F, has 0 mean, you'll have a solution, but that solution will not be unique. What you could do is impose a condition on U, that if you require that U also have 0 mean, then U hat 0, 0 would have to be 0. So that's one way to, the point is you need to impose another condition to get a unique solution. All right. So these kind of PDE, it's very easy to solve numerically. So those like steps I gave you before. So F hat is 2-dimensional FFT. F hat F hat over a third of L squared. And then U is inverse FFT 2-dimensional of U hat. And you're done. And the smoother F is, the more accurate the solution will be. All right, questions about this, or we have time? Homework questions. Whatever you got. But if you want to know how our homework is coming. Has anyone touched a MATLAB problem? Okay.
That's yes.
All right. Fine with me. Okay. Yeah, so Thursday I'll talk about Chebyshev spectral methods for a non-periodic case. And we'll certainly have time then. If anybody can spend time between now and then, and doesn't matter to me. Because there'll also be time later, but okay. More free time for us then.